Everyone, myself Prashant Patil, rule number 131. Today our group presenting the implementation of BCD to XS3 code and also a converter which converts BCD to XS3 code, also it reverse XS3 code to BCD. So let's start. So this is the outline of our topic: introduction, problem statement, truth table, K-map, circuit diagram. So first we see introduction. Before starting introduction, we see some basic concepts like decimal number, binary, BCD, access code, weighted code, non-weighted code. First we see decimal number. As we know, decimal number is a number which have base 10 or it is used in every daily life. Binary code. Binary code means meaning two. As we know, bicycle, binocular. Bicycle means two wheels. Binocular means two eyes. As we know, also binary only uses of two digit 1 and 0. So next is BCD. BCD's full form is binary coded decimal, where weighted code, where each, as we know, binary code decimal is a weighted code, or weighted code it means where each digit position is being assigned to a specific weight. And also there is a non-weighted code. Non-weighted code means no positional weight, or also there is example of non-weighted code is the XS3 code. XS3 code means words are derived the 8 4 to 1, like BCD code words adding 3 to it. It's called XS3 code. So let's start to our introduction. As we know, the decimal to BCD converter used to convert a decimal integer to BCD. So how to binary coded to decimal? In a computing and electronic system, a binary decimal is a digital encoding method for a decimal number in which each digit represented by its own binary sequence. BCD is a different from converting a decimal to binary. For example, 45. When we convert binary, it is 101101 and it is represented in BCD 01000101. As we see how to convert a binary into BCD or also decimal.
Hi, I am Harshal Dhankar, roll number 112. Now we see the problem statement: design and implement BCD to XS3 code converter and XS3 to BCD code converter. So here we have input like 8, 4, -2, -1. Hence the number of input is 4, and in BCD code output is 4. Hence the number of output is 4. So next we go for the truth table. If we want to find decimal binary code of 6 in 8 4 -2 -1, sum of 8 and -2 is 6. Hence on 8 and -2 it means 8 and -2 becomes 1 and remaining 4 and -1 becomes 0. And if we want to find its related output in BCD code, so we get 0110 binary code in BCD coding scheme. Similarly, we take another decimal number. So next, if we want to find the decimal number 3 in 8 4 -2 -1, so the sum of 4 and -1 is 3, and hence 4 and -1 becomes 1 and remaining 8 and -2 becomes 0, and we get 0101 binary code in 8 4 -2 -1 coding scheme. If we want to find its related output in BCD code, so we get 0011 binary number. Similarly for 2 in 8 4 -2 -1, so the sum of 4 and -2 is 2. Hence 4 and -2 becomes 1 and remaining consider as 0. And we get 0110 in 8 4 -2 -1. If we want to find its related output in BCD code, so we get 0010 in BCD code, because binary code for 2 is 0010. Similarly, we find for all the decimal numbers. So this is how the code converter works: 8 4 -2 -1 to BCD code. We try to explain using the truth table.
So on the basis of truth table, we find don't care term represented by cross. Here the don't care terms that does not part in decimal number means here 0000, like this is the take part in the condition here 0 0 0 and 0. So the don't care terms are 1 2 3 12 13 and 14. When we last solve this, then the don't care terms are 1 2 3 12 13 14. So this is the given K map for the truth table of W. Here 8 and 15 are represented by 1. Here also the 8 and 15 are represented by 1 as shown in figure. So the given output is W is equal to AB. Here W is equal to AB for 1 1 and plus AC dash D dash. W is equal to AB for this given and AC dash is for that X and 1. Now we move towards the another operation, that is on X. Here the output 1 is on 4 5 6 and 7. Here we represent 1 for 4 5 6 and 7, and here we do pair grouping, here also pair grouping, and here another pair grouping. So the given output is that X is equal to B dash C plus B dash D plus B C D dash. Next, here when we go for Y, then the 1 are represent for 2 3 6 and 7. As shown, there is 2 3 6 and 7. We find that the output is C dash D plus CD dash, as the quad grouping is 1 for, and the last one is Z. For the Z, the output 1 is for on 1 3 5 and 7. Here 1 3 5 7 9. Here octal grouping is made, and the given output is Z is equal to D. Thank you.
So after obtaining the K-map equation, we will get the 4 K-map equation W, X, Y, Z. Now we will draw the circuit diagram for the given K-map equation. So first equation is equal, W is equal to A into B plus A into complement of C into complement of D. So here we will use 2 AND gate and 1 OR gate. So we'll connect the input of the first AND gate to here we have 4 input A B C D. So we'll connect the input of the first AND gate to A and B, and or the input of the second AND gate we will connect A complement of C into complement of D, and output of this two AND gate we will connect to the OR gate, and we will get the first K-map equation W. Now we will draw the circuit diagram for the second K-map equation. X equal to complement of B into C plus complement of B into D plus B into complement of C into complement of D. So here we will use 3 AND gate and 1 OR gate. So we will connect the input of the first AND gate complement of B into C, and input of the second AND gate we will connect the complement of B into D input, and for the input of the third AND gate we will connect the input of B into complement of C into complement of D, and output of these 3 AND gate we will connect to the OR gate, and from this we will get the equation for the third K-map equation X. Now we will draw the circuit diagram for the third K-map equation Y equal to complement of C into D plus C into complement of D. So here we will use a 2 AND gate and 1 OR gate. So we will connect the input of the first AND gate to complement of C, and second input is D, and the input for the second AND gate we will connect the C and second input is complement of D. So output of the these 2 AND gate we will connect to the OR gate, and output of this OR gate we will get the third K-map equation Y. So for the KMAP equation is equal to Z equal to D. So here we will not use any gates. We will directly connect D, and we will get the third KMAP equation Z.
Hello everyone, my name is Yash Devkar, roll number 106. My friend already discussed about the KMAP, truth table and circuit diagram about our topic, that is the combinational circuit, design and implementation of combinational circuit which converts 84-2-1 decimal code into BCD code. So we will see the actual execution of our circuit. Firstly, we will take two nodes as a power supply, and we will put the grounds all the ICs. We required one NOT IC, two AND ICs, and two OR ICs. After that, for output we need four resistors and four LEDs to execute this circuit. So firstly we will put down the ground. For every IC, after adding all the grounds we will have to add VCC for every IC. So friends, now implementing all the wires and in the ICs and all implementing all the lights, we will have four inputs as ABCD. So we will verify now the truth table. So we will directly take the ninth condition, that is we will take A, B, C, D as 1. So we will get first and fourth light as a glow. So this is A as 1, and this is C, that is B, this is D. So we took all the nodes as 1. So here is the output, first and fourth light is glow. Now in second case we will see the sixth case, that is A and C as 1s. So we will get output as second and third light as glow. So after taking only A as 1 and C as 1, then B and D are in zeros. So B and D as zeros. So we got, according to truth table, second and third light is glow.